some polynomial functions have imaginary or complex zeros, and so we can't find these by synthetic division. So what does that mean for a graph? Well, if I have a cubic function, so let's say the highest exponent was x cubed in there, but then I graphed it, and I took that function and I ended up with a graph that looks like this. When I look at that graph, I only see the evidence of one real zero, but I'm supposed to have 3 if my highest exponent is 3. And so the clue that this function would have some imaginary zeros, a pair of imaginary zeros to go with the one real, is what's going on in this dip over here that doesn't make it all the way to the x-axis. You can think of it as it doesn't have enough oomph to get us all the way down there. And so in that circumstance, what that means is we have some evidence of there being complex or imaginary zeros, because we have to have 3 zeros, but if I only have the one here that is evidence of a real zero, the others must be imaginary. Now I can't look at the graph and say, my other zeros are 2 plus 5i and 2 minus 5i or something like that. But I know that there are some complex zeros that I'm going to have to find somehow. And the only way we're going to be able to do that is by finding the real zeros and then solving the equation that's left behind using some factoring or quadratic formula or completing the square technique. So if we look at this complex conjugates theorem, we at least get a little assistance on these complex zeros, that they always come in conjugate pairs. So just like irrational zeros, like a square root 0 comes in conjugate pairs, so too do these imaginary zeros. They always come in conjugate pairs if your polynomial function has integer coefficients like the one that we see in front of us. So on this one here, we're told that we've got this polynomial function x to the 4th plus x squared minus 12, and we're also told that 2i is a zero. But by implication, based on this complex conjugates theorem, that also means that negative 2i is a zero. But that still means I've got a couple other zeros that are hanging out there, so I need to find those somehow. Now they might be real, so I could use my p over q list and then generate a list of zeros and try to find them via synthetic division, but they might not be real. They might also be imaginary, or they might be irrational. So it's no guarantee that that work would actually lead me to the remaining zeros. So instead we can take a slightly different approach. We can instead say, all right, if these two are zeros, then we know that x minus 2i and x plus 2i are both factors of this polynomial function. So then, if I can figure out what I need to multiply those two factors by to get back to my original function, well, then I'm going to have we know that that's going to have to be an x squared polynomial because I have to end up at x to the 4th. So then this remaining polynomial is going to be one that I can solve using quadratic techniques to find those remaining zeros. So how do I find what this missing quadratic is? Well, what I'm going to do over here is I'm going to FOIL out this x minus 2i times x plus 2i. If I do that, and we can see we have a difference of squares pattern, so I can go ahead and just multiply the firsts and multiply the lasts. So I'm going to get x squared minus 4i squared. But of course, I squared gets replaced with negative 1. So we're ending up with x squared plus 4 when I multiply those two known factors out. And so now, that means that x squared plus 4 times this missing quadratic has to get us back to our original function. Or, what I could say is, take that original function, divide it by x squared plus 4, and then that will leave me with the quadratic that I can then solve. But unfortunately, I'm not going to be able to use synthetic division to perform this division because synthetic division only works if it's x plus or minus some number, not if it's x squared. So I am going to have to engage in some long division on this one. But we'll manage. So I'm going to try to squeeze this in over here. Let me clear a little space for us. And so we can get started. So I've got x squared plus 4 is my divisor, and then my original polynomial function, x to the 4th, need my placeholders, plus 0x cubed, plus x squared, plus 0x, and then minus 12. I need those two placeholders for the missing terms. Now I can do my long division. So recall it's x squared times what equals x to the fourth. That, of course, is going to be x squared. We knew that x squared was going to be our starter here based on the function that we're working with. So now I distribute x squared times x squared is x to the fourth plus 4x squared. Now I'm ready to subtract. My x to the fourths cancel out. I don't have any x cubes, so I just have to subtract the x squareds. X squared minus 4x squared gives us negative 3x squared. And then I'm going to bring down my negative 12. I can also bring down my 0x, but I'll just bring down my negative 12 as well. And so now x squared times what equals negative 3x squared? Well, that's going to be negative 3. And so, well, I can put that over my like term here. So negative 3 times x squared is indeed negative 3x squared. And then negative 3 times 4 is negative 12, lining up my like terms here. And so we can see we got the same thing, which we should because we knew that this would divide in evenly based on the information that these were zeros of our polynomial function. So that means I get no remainder. So that means my missing polynomial here that I need to multiply x squared plus 4 by to get back to my original is x squared minus 3. And so now I'm going to take that x squared minus 3, I'm going to set it equal to 0 to find the remaining zeros of this polynomial function. So I can't factor that because 3 is not a perfect square, so even though it sets up as a difference of squares type question, 3 is not a perfect square. So I'm going to have to solve using square roots. I can add 3 to both sides, so I get x squared equals 3. And so now I can take the square root of both sides, and so indeed I am not getting rational zeros. So if I had tried to use my P over Q approach, it would have led me nowhere on this one. So I get my remaining two zeros are plus or minus root 3. So altogether, I have my 4 zeros, the 2i that was given, the negative 2i that has to be a 0 since those imaginary zeros always come in conjugate pairs, and then to go with those two, we solved using this approach of foiling the known factors, long dividing it into the polynomial function to get the remaining quadratic, which led us to positive and negative root 3 as our remaining zeros.